In the vast cosmic darkness, where light itself struggles to find meaning across billions of years of travel, there exists something that should not be. A region of space so empty, so profoundly devoid of matter and energy, that it appears to punch a hole through the very fabric of space-time itself. This is not merely an absence, it is an anti-presence, a cosmic wound that challenges the most fundamental assumptions about how the universe came to be. The cold spot, as astronomers have come to call it, spans nearly 1 billion light-years across the southern sky. To comprehend this scale, imagine that our entire Milky Way galaxy, with its 400 billion stars, its spiral arms reaching 100,000 light-years from edge to edge, is but a grain of sand. The cold spot would be a football stadium carved from nothing but emptiness, suspended in the cosmic web like a tear in reality itself. Within its boundaries, temperatures drop by 70 microkelvins below the cosmic microwave background, the afterglow of the Big Bang that permeates all of space. To human senses, this difference would be imperceptible, lost in the absolute cold that grips the universe at 2.7 degrees above absolute zero. But to the cosmos, this temperature depression represents an anomaly so severe that it threatens to rewrite the laws of cosmic evolution. When astronomers gaze into this void through their most sophisticated instruments, they are not simply observing empty space. They are staring into a mystery that suggests our universe may be connected to something else, perhaps another universe entirely, or a realm where different physical laws govern reality. The cold spot appears to be a scar left by a collision with another cosmos, a cosmic bruise that has persisted for over 13 billion years, since the universe was young enough for such impossible encounters to occur. This discovery forces humanity to confront an unsettling possibility that our universe is not the closed, complete system we believed it to be, but rather one bubble in an infinite foam of realities. And if other universes can leave their mark on ours, what else might be seeping through the cracks in space-time? What other impossible things await discovery in the seemingly empty spaces between the stars? The cold spot defies the very foundations of cosmological understanding. According to the standard model of cosmic evolution, such extreme voids should not exist. Matter should be distributed more evenly throughout space, following the delicate patterns imprinted during the universe's first moments. Yet here lies something that appears to violate these sacred principles, a region where the normal rules of physics seem to break down, where the universe itself bears the wound of an encounter with the impossible. The story begins not with a telescope pointed at distant galaxies, but with an accidental discovery that would revolutionize humanity's understanding of cosmic origins. In the summer of 1965, 2 radio astronomers working at Bell Labs in Holmdel, New Jersey, stumbled upon the most important signal in the history of science. Arno Penzias and Robert Wilson were attempting to eliminate background noise from their sensitive radio antenna when they discovered something extraordinary. A faint, persistent hiss coming from every direction in the sky. This signal, they would learn, was the cosmic microwave background radiation, the ancient afterglow of the Big Bang that fills every corner of space. It represented the universe as it was merely 380,000 years after its creation, the moment when space became transparent and light could finally travel freely across the cosmos. For the first time, scientists could see the universe as an infant, still glowing with the heat of its violent birth. The cosmic microwave background carries within its subtle variations a map of the early universe's temperature fluctuations, tiny differences in density that would eventually grow into the galaxies, stars, and planets that populate space today. These fluctuations are remarkably small, typically varying by only a few parts in 100,000. The universe's baby picture reveals an almost perfectly smooth cosmos, with only the faintest wrinkles that would later blossom into the rich structures we observe today. For nearly 4 decades after its discovery, the cosmic microwave background remained frustratingly uniform. Ground-based telescopes and early satellites detected only the largest scale variations, confirming that the early universe was indeed remarkably smooth. Scientists assumed that this smoothness would extend to the smallest observable scales, with only tiny, statistically predictable variations scattered across the sky. In 2001, NASA launched the Wilkinson Microwave Anisotropy Probe, known as WMAP, to create the most detailed map of the cosmic microwave background ever attempted. From its position at the L2 Lagrange point, 1.5 million kilometers from Earth, WMAP began systematically scanning the entire sky with unprecedented precision. As data streamed back over the course of 9 years, a pattern began to emerge that would challenge everything cosmologists thought they knew about the universe. The satellite's instruments detected the expected tiny fluctuations across most of the sky, hotspots and cold spots that differed by mere microkelvin, perfectly consistent with theoretical predictions. But nestled within the southern hemisphere, in the constellation Eridanus, lay something that defied all expectations. Here was a region nearly 30 degrees across, roughly 60 times the apparent size of the full moon, where the temperature was significantly colder than anywhere else in the observed universe. Lawrence Rudnick at the University of Minnesota was among the first scientists to recognize the profound implications of this discovery. While studying radio galaxies in 2004, he noticed an unusual absence of radio sources in the same region where WMAP had detected the temperature anomaly. Where hundreds of radio galaxies should have been visible based on surveys of other regions, there were virtually none. The cosmos appeared to contain a vast, empty space, not just devoid of visible matter, but seemingly empty of nearly everything. When researchers cross-referenced Rudnick's radio observations with the WMAP temperature data, the correlation became undeniable. The largest temperature anomaly in the cosmic microwave background coincided perfectly with the most extreme void in the galaxy distribution. Something had carved a hole in the universe so vast and so empty that it left its signature in the very fabric of space-time itself. The initial measurements of the cold spot seemed to violate everything cosmologists understood about the universe's structure and evolution. The anomaly stretched across 1.8 billion light-years of space, roughly 10,000 times larger than the Milky Way galaxy, and containing enough volume to hold millions of galaxy clusters. Within this region, galaxy density dropped by approximately 20% below the cosmic average, creating what appeared to be the largest known structure in the observable universe. But it was not the size alone that shocked the scientific community. It was the magnitude of the temperature depression. According to the standard model of cosmology, such a vast void should indeed appear slightly cooler than its surroundings due to a phenomenon known as the integrated Sachs-Wolf effect. As photons from the cosmic microwave background travel through regions of varying gravitational potential, they gain and lose energy in predictable ways. Light climbing out of gravitational wells loses energy and becomes redder and cooler, while light falling into wells gains energy and becomes bluer and hotter. A large void with its reduced matter density and weaker gravitational field should create a subtle cooling effect on the cosmic microwave background. The calculations were straightforward. Even the largest possible voids predicted by standard cosmology should create temperature depressions of perhaps 10 to 20 microkelvins at most. These would be detectable but not remarkable, natural consequences of the universe's lumpy structure. The cold spot registered a temperature depression of 70 microkelvins, more than 3 times what the most generous theoretical models could explain. This discrepancy might seem minuscule to human perception, but in the precisely calibrated universe revealed by cosmological observations, it represented a catastrophic failure of established models. The probability of such a temperature fluctuation occurring naturally through the standard processes of cosmic evolution was calculated to be less than 1 in 50,000, making it one of the most statistically significant anomalies ever detected in astronomical data. Even more disturbing was the spot's apparent age. The cosmic microwave background represents conditions from when the universe was only 380,000 years old, long before the first stars ignited, before galaxies formed their spiral structures, before planets condensed from stellar debris. The universe at this epoch was still glowing with the heat of creation, its matter distributed in an almost perfectly uniform plasma that had only just cooled enough for atoms to form. Yet the cold spot's signature was already imprinted in this ancient radiation, embedded in the fundamental structure of spacetime like a birthmark on the cosmos. This meant that whatever created this anomaly had to have been present from the very earliest moments of cosmic history, not something that developed through the slow accumulation of matter into galaxies and voids, but a primordial feature written into the universe's initial conditions. The implications were staggering. If the cold spot truly represented a primordial anomaly, it suggested that the universe's birth was far more violent and chaotic than previously imagined. The smooth, symmetric expansion predicted by inflation theory, the rapid expansion that supposedly smoothed out irregularities in the early universe, seemed inadequate to explain such an extreme deviation from uniformity. Dr. Istvan Shapudi of the Institute for Astronomy at the University of Hawaii described the discovery as the largest individual structure ever identified by humanity, but calling it a structure seemed somehow inadequate, even misleading. This was not something built or assembled through natural processes, but rather something missing, something carved away from the cosmic tapestry by forces that operated beyond the known laws of physics. The cold spot challenged the very notion that the universe was comprehensible through human reason and scientific methodology. Here was a phenomenon that violated the principle of cosmic democracy, the assumption that all regions of space should be fundamentally similar, governed by the same physical laws and shaped by the same cosmic processes. Instead, the universe appeared to contain a region where different rules applied, where the normal constraints of physics had been suspended or overridden by something even more fundamental. As more sophisticated instruments came online throughout the 2000s and 2010s, the true scope of the cold spot's mystery began to reveal itself in unprecedented detail. What had initially appeared to be a simple spherical void turned out to be far more complex and disturbing, a hierarchical structure of emptiness that seemed to extend across multiple scales of cosmic organization. The Dark Energy Survey, which began operations in 2013 using the 4-meter Victor M. Blanco telescope in Chile, provided the first detailed three-dimensional mapping of galaxy distributions across the southern sky. What it revealed about the cold spot defied conventional understanding of how cosmic voids form and evolve. Rather than a single, uniform, empty region, the anomaly possessed a complex, nested structure that astronomers termed a super void. At the heart of this cosmic abyss lay an even more extreme emptiness, a core region spanning 220 million light-years where galaxy density dropped by 80% below the cosmic average. This central void was surrounded by concentric shells of increasingly normal galaxy density, extending outward like ripples frozen in spacetime. The pattern resembled the aftermath of a cosmic impact, as if something had struck the universe with such force that it displaced matter across scales previously thought impossible for a single event. Radio telescope surveys conducted with the Australia Telescope Compact Array and the Very Large Array revealed additional layers of mystery. These instruments detected significant radio source underdensities extending far beyond the optical void boundaries, suggesting that the cold spot's influence on matter distribution reached across scales that challenged the fundamental assumptions of cosmic structure formation. The void appeared to have been carved directly from the cosmic web, the largest scale scaffolding of dark matter filaments that guides galaxy formation throughout the universe. Even more puzzling was the discovery of the void's apparent motion through space. Detailed analysis of the cosmic microwave background data revealed that the cold spot exhibited a peculiar, proper motion across the sky. It appeared to be drifting relative to the overall cosmic reference frame at a velocity of several hundred kilometers per second. This motion was completely unexpected, as primordial features should remain fixed relative to the cosmic microwave background. The drift suggested that whatever created the void had also imparted momentum to it, as if the universe had been struck by something massive, moving at incredible speed. The impact had not only carved out the void, but had set it in motion through spacetime, creating a cosmic scar that continued to migrate across the sky billions of years after its formation. High-resolution temperature maps created by combining data from multiple missions, WMAP, the European Space Agency's Planck satellite, and ground-based interferometers, revealed fine-scale structure within the cold spot that resembled the fingerprints of a cosmic collision. Concentric temperature rings, asymmetric heating patterns, and linear temperature gradients all pointed to an external influence rather than natural evolution from primordial quantum fluctuations. The Planck satellite, operational from 2009 to 2013, provided the highest resolution map of the cosmic microwave background ever created, confirming the cold spot's existence with unprecedented precision. Planck's measurements revealed additional fine-scale structure that earlier missions had missed, including subtle polarization patterns in the microwave radiation, the orientation of electromagnetic waves that carry information about the physical processes that created them. Within the cold spot, these polarization patterns showed signs of distortion that suggested the influence of exotic physics operating beyond the standard model of cosmology. The patterns appeared to spiral inward toward the void's center, as if the fabric of spacetime itself had been twisted by whatever force created the anomaly. Some researchers compared these patterns to the event horizon of a black hole, where space and time become so warped that normal causality breaks down. Ground-based interferometers, including the South Pole Telescope and the Atacama Cosmology Telescope, focus their attention on the cold spot region, seeking to measure temperature fluctuations on even smaller angular scales. These observations revealed that the anomaly maintained its statistical significance across all measurable scales, from the largest features detectable by space-based satellites down to the smallest fluctuations accessible to ground-based instruments. This scale-invariant behavior was precisely what would be expected from a primordial origin, something imprinted on the universe at the moment of creation rather than developed through the gradual evolution of cosmic structure. It suggested that the cold spot was not merely an unusual arrangement of matter and energy, but a fundamental feature of space-time itself, woven into the very geometry of the universe during its first moments of existence. By 2015, accumulating evidence forced cosmologists to confront an extraordinary possibility that challenged the most basic assumptions about the nature of reality itself. The cold spot, with its impossible size, its extreme temperature depression, its complex internal structure, and its mysterious motion through space, could not be explained by any known process within our universe. The only hypothesis that could adequately account for the full range of observed phenomena was almost too radical to contemplate. The cold spot might represent physical evidence of our universe's collision with another universe. Laura Mersini Houghton of the University of North Carolina, a theoretical physicist who had predicted such anomalies in the cosmic microwave background as early as 2005, argued that the void bore the unmistakable signature of inter-universal contact. Her calculations, based on string theory and the mathematics of eternal inflation, suggested that our universe should indeed show scars from encounters with neighboring cosmos during the first fraction of a second after the Big Bang. According to Mersini Houghton's analysis, the cold spot's size, temperature depression, internal structure, and motion all matched theoretical predictions for what a universe-to-universe collision would produce in the cosmic microwave background. During the period of cosmic inflation, when our universe expanded exponentially from quantum scale to cosmic proportions in less than a trillionth of a second, it would have been small enough to come into contact with other inflating universe bubbles. The implications were staggering beyond human comprehension. If the cold spot truly represented a collision with another universe, it meant that our cosmos was not an isolated entity, but part of a vast multiverse, an infinite collection of bubble universes constantly expanding, colliding, and influencing each other across dimensions that human consciousness could barely grasp. The collision hypothesis explained not only the void's extreme temperature depression, but also its hierarchical structure and apparent motion through space. The impact would have displaced matter and energy in our early universe, creating complex patterns of density fluctuations that would eventually evolve into the nested voids observed today. The momentum of the collision would account for the cold spot's drift across the cosmic microwave background, while the collision's energy would explain the extreme deviations from thermal equilibrium. Computer simulations of universe-to-universe collisions conducted at major research institutions, including Cambridge University and the Perimeter Institute, produced cosmic microwave background signatures remarkably similar to the observed cold spot. These simulations modeled the physics of two inflating universe bubbles coming into contact, tracking how the collision would affect the distribution of matter and energy in both cosmos. The results were haunting in their implications. The simulations showed that such collisions would indeed create vast voids in one or both universes, accompanied by temperature depressions in the cosmic microwave background that could persist for billions of years. The collision would leave behind a permanent scar, a reminder that our universe had once touched something utterly alien, something governed by potentially different physical laws and populated by forms of matter and energy that might be impossible within our cosmic domain. Additional support for the multiverse collision theory came from the cutting edge of theoretical physics. String theory, which attempts to unify quantum mechanics with general relativity by describing fundamental particles as vibrating strings in higher dimensional space, naturally predicted the existence of multiple universes. In the string theory landscape, our universe would be just one of perhaps 10,500 possible vacuum states, different ways that the fundamental forces and particles could be arranged. Eternal inflation, another leading theory in cosmology, suggested that the process of cosmic expansion might be ongoing and infinite, constantly creating new universe bubbles in an ever-expanding multiverse. In this scenario, collisions between universe bubbles would not only be possible, but inevitable. Our universe would be surrounded by countless others, each with its own history, its own physical constants, and its own potential for complexity and life. The multiverse collision hypothesis also provided a natural explanation for several other anomalies in the cosmic microwave background that had puzzled astronomers for years. The so-called axis of evil, an unexpected alignment of temperature fluctuations on the largest scales, could represent another signature of inter-universal contact. The mysteriously low amplitude of fluctuations on certain scales might indicate that our universe's initial conditions were influenced by external forces. Yet even as evidence mounted in favor of the collision hypothesis, many scientists remained skeptical. The multiverse, by its very nature, seemed to lie beyond the reach of experimental verification. If other universes were truly separate from our own, separated by the fundamental structure of space-time itself, how could their existence ever be definitively proven? The cold spot might represent the first and only direct evidence of other realities, a cosmic message in a bottle that had washed up on the shores of our observable universe. While the multiverse collision theory captured the imagination of physicists and the public alike, the scientific community proposed several competing explanations for the cold spot, each more extraordinary than the last. These alternative hypotheses all pointed beyond the boundaries of conventional physics, toward phenomena that operated on scales and in dimensions that human science had never directly accessed. One of the most intriguing possibilities involved cosmic strings, theoretical one-dimensional defects in space-time predicted by many unified field theories. These strings, if they existed, would be remnants of the universe's first moments, when the fundamental forces of nature were still unified in a single, symmetric field. As the universe cooled and expanded, this unified field would have undergone a series of phase transitions, similar to the way water crystallizes into ice, potentially leaving behind linear defects in the fabric of space-time itself. A cosmic string passing through our early universe could have carved out the observed void through its immense gravitational effects. Despite being thinner than a proton, such a string could possess the mass of an entire galaxy stretched across its length. As it moved through space at nearly the speed of light, it would have swept matter aside like a cosmic bulldozer, creating the vast, empty region we observe today. The temperature signature of a cosmic string passage would indeed match many features of the cold spot. The string's gravitational field would create exactly the kind of temperature depression observed in the cosmic microwave background, while its motion through space would account for the void's apparent drift across the sky. Computer simulations of cosmic string networks showed that they could indeed create structures as large and as empty as the cold spot, leaving behind signatures that would persist for billions of years. Perhaps most exotic was the wormhole hypothesis, proposed by several theoretical physicists working at the intersection of general relativity and quantum mechanics. Some researchers suggested that the cold spot might mark the mouth of a traversable wormhole, a tunnel through spacetime connecting our universe to another region of reality. Such structures were permitted by Einstein's equations under certain exotic conditions, though they would require forms of matter with negative energy density that had never been observed in nature. Matter and energy flowing through such a wormhole could account for the void's properties, while the wormhole's gravitational effects would create the observed temperature depression in the cosmic microwave background. The wormhole mouth might appear as a spherical region where the normal laws of physics were suspended, where matter could disappear into another universe entirely, leaving behind only gravitational shadows and temperature anomalies. The holographic principle, derived from black hole thermodynamics and string theory, offered yet another perspective on the cold spot mystery. This radical idea suggested that our three-dimensional universe might actually be a holographic projection of information encoded on a two-dimensional surface at the cosmos boundary. In this view, all the matter, energy, and space-time we experience would be emergent properties of underlying informational patterns. If the holographic principle were correct, then the cold spot might represent a region where this holographic encoding had been disrupted, a cosmic glitch in the information matrix that defines our reality. The void would not be empty in the conventional sense, but rather a region where the holographic projection had become corrupted or incomplete, creating the appearance of missing matter and energy. Quantum field theory provided another set of exotic explanations for the cold spot. Some theorists proposed that the void might be associated with a false vacuum decay event, a region where the quantum fields that fill empty space had tunneled to a lower energy state. Such a transition would create an expanding bubble of altered physics, within which the fundamental constants of nature might be different from their values in the surrounding universe. If a false vacuum decay bubble had formed in our early universe and then stopped expanding for some unknown reason, it could have left behind the kind of signature observed in the cold spot. The altered physics within the bubble would affect how matter and energy behaved, potentially creating the observed void and temperature depression, while maintaining its distinct properties across cosmic time. Each of these alternative explanations carried profound implications for our understanding of reality. Cosmic strings implied that the universe contained linear defects that could stretch across cosmic distances, connecting the smallest scales of physics to the largest structures in space. Wormholes suggested that space and time might be navigable in ways that could revolutionize our concepts of causality, locality, and the nature of existence itself. The holographic principle pointed toward a reality where everything we experience might be fundamentally illusory, a three-dimensional shadow cast by information existing in fewer dimensions. False vacuum decay raised the possibility that the very laws of physics might be mutable, subject to quantum transitions that could alter the fundamental nature of reality across vast regions of space and time. The quest to understand the cold spot has driven the development of increasingly sophisticated observational tools and theoretical frameworks, pushing the boundaries of what human technology can achieve in the service of cosmic understanding. Modern cosmology has marshaled its most advanced instruments to peer deeper into this cosmic mystery, each observation adding new layers of complexity to an already bewildering phenomenon. The European Space Agency's Planck satellite, which operated from 2009 to 2013, provided the highest resolution map of the cosmic microwave background ever created. From its vantage point at the L2 Lagrange point, Planck systematically scanned the entire sky with 9 frequency bands, achieving temperature sensitivity of just a few microkelvin and angular resolution of a few arc minutes. The satellite's measurements not only confirmed the cold spot's existence with unprecedented precision, but revealed additional fine-scale structure that earlier missions had completely missed. Planck detected subtle polarization patterns in the microwave radiation, the orientation of electromagnetic waves that carry information about the physical processes that created them. These polarization measurements provided a new window into the cold spot's origins, revealing how the early universe's magnetic fields and plasma motions had been affected by whatever created the void. The patterns showed signs of distortion that suggested the influence of exotic physics operating far beyond the standard model of cosmology. Ground-based interferometers have joined this cosmic investigation, using arrays of radio telescopes to achieve even higher resolution observations of specific regions of the sky. The South Pole Telescope, operating in the pristine Antarctic environment where atmospheric interference is minimal, has focused its attention on the cold spot region with remarkable results. Its measurements reveal that the anomaly extends down to the smallest measurable angular scales, maintaining its statistical significance across all resolution levels observed. The Atacama Cosmology Telescope, positioned at an altitude of 5,190 meters in Chile's Atacama Desert, has provided complementary observations that confirm the cold spot's reality across multiple frequency bands. These measurements have ruled out several alternative explanations for the anomaly, including the possibility that it results from instrumental effects or foreground contamination from our own galaxy. The Dark Energy Survey has continued its ambitious mapping of galaxy distributions across the southern sky, using gravitational lensing techniques to probe the cold spot's three-dimensional structure with unprecedented detail. By measuring how the gravity of the supervoid bends light from background galaxies, astronomers have created detailed maps of the mass distribution within the anomaly. These maps reveal that the void's gravitational influence extends even further than its visible emptiness, suggesting either the presence of undetected dark matter structures or fundamental modifications to gravity itself. The James Webb Space Telescope, humanity's most powerful space observatory, has turned its infrared eyes toward the cold spot region, searching for clues that might have been invisible to previous generations of instruments. Webb's unprecedented sensitivity allows it to peer deeper into cosmic history than ever before, potentially detecting primordial galaxies within the void that might reveal how this cosmic anomaly formed and evolved over billions of years. Future missions promise even greater insights into the cold spot mystery. The Nancy Grace Roman Space Telescope, scheduled for launch in the mid-2020s, will conduct the largest galaxy survey in history, mapping the distribution of matter across the observable universe with exquisite precision. Its wide field of view and high sensitivity will allow astronomers to map the cold spot's boundaries and internal structure in 3 dimensions, potentially revealing whether it connects to larger structures in the cosmic web. The Euclid Space Telescope, launched by the European Space Agency, is simultaneously mapping the geometry of the universe through gravitational lensing measurements. Its observations of the cold spot region will provide independent confirmation of the void's mass distribution while searching for subtle signs of modified gravity or dark energy interactions that might explain the anomaly's extreme properties. Perhaps most ambitiously, scientists are developing new theoretical tools designed to test multiverse hypotheses directly. Research teams at institutions including Harvard, MIT, Stanford, and Cambridge are working on sophisticated models that predict specific observational signatures of universe-to-universe collisions, cosmic strings, and higher dimensional physics. These models are being refined to make testable predictions about the polarization patterns, temperature distributions, and matter densities that each exotic scenario would produce. Advanced computer simulations running on the world's most powerful supercomputers are modeling the formation and evolution of cosmic voids under various physical scenarios. These simulations can track the behavior of matter and energy across cosmic time, testing whether conventional physics can produce structures as extreme as the cold spot, or whether exotic explanations are truly required. Machine learning algorithms are being trained to search for additional anomalies in the cosmic microwave background and galaxy survey data that might represent other signatures of exotic physics. These artificial intelligence systems can identify patterns and correlations that human researchers might miss, potentially uncovering additional evidence for multiverse interactions, cosmic strings, or other exotic phenomena. The hunt for understanding has also driven advances in theoretical physics itself. String theorists are developing new mathematical tools to calculate the expected signatures of universe-to-universe collisions, while cosmologists are exploring how modifications to inflation theory might account for primordial anomalies like the cold spot. In the end, the cold spot forces humanity to confront the most fundamental questions about existence, reality, and our place in the cosmic order. This billion light-year wound in space-time has transcended its role as a mere astronomical curiosity to become something far more profound. A window into the deepest mysteries of being itself, a cosmic koan that challenges every assumption about the nature of reality. The implications ripple outward from the cold spot like expanding waves through the ocean of human consciousness. If this anomaly truly represents evidence of other universes, then everything we thought we understood about the uniqueness and completeness of our reality must be reconsidered with the humility that comes from glimpsing the infinite. For millennia, humans have lived with the assumption that our universe, with its specific physical constants, its particular history of stellar birth and death, its unique arrangement of matter and energy that allowed for the emergence of complexity and consciousness, was all that existed. The cold spot whispers of a different truth. It suggests that we inhabit merely one cosmic bubble in an infinite foam of realities, each with its own laws of physics, its own story of creation and evolution, its own potential for life and consciousness to emerge from the dance of matter and energy. Our universe, vast beyond human comprehension, containing hundreds of billions of galaxies, each populated by hundreds of billions of stars, might be just one note in an infinite cosmic symphony. This realization carries profound implications for how we understand meaning and purpose in our lives. Are we significant beings in a universe that is one among countless others? Does consciousness, that most precious and mysterious emergent property of complex matter, arise inevitably in any universe with the right conditions? Or does the multiverse hypothesis actually enhance our significance, suggesting that we are witnesses to something even more extraordinary than previously imagined? The first direct evidence that reality itself is far more vast, strange, and interconnected than our ancestors ever dared dream. The cold spot also represents a humbling reminder of the vast expanses of ignorance that still surround our small islands of scientific knowledge. Despite centuries of unprecedented progress, despite our sophisticated theories about quantum mechanics and relativity, despite our powerful instruments that can detect temperature variations of microkelvin across billions of light years, we remain cosmic children puzzling over phenomena that dwarf our understanding. The universe continues to surprise us, to challenge our assumptions, to reveal new depths of mystery, just when we think we have grasped its essential nature. Each answer leads to deeper questions. Each discovery unveils greater mysteries. The cold spot reminds us that the cosmos is under no obligation to be comprehensible to human minds, that reality extends far beyond the boundaries of our direct experience, and perhaps beyond the ultimate limits of our capacity for understanding. Perhaps most poignantly, the cold spot embodies both our cosmic loneliness and our cosmic connection in ways that previous generations could never have imagined. If other universes truly exist, if the multiverse hypothesis represents reality rather than mathematical speculation, then we are simultaneously more isolated than we ever feared, and more connected than we ever hoped. We are isolated because these other realities remain fundamentally inaccessible to us, separated not merely by distance, but by the very structure of space-time itself. The other universes that may have left their mark in our cosmic microwave background exist in a realm that we can never visit, never directly observe, never truly comprehend. They remain forever beyond our reach, like islands of reality in an ocean of possibility that we can never cross. Yet we are also connected in the most profound way imaginable. The cold spot suggests that our universe has been touched by something external, that the boundary between our reality and others is not impermeable. We carry within our cosmic DNA the signature of contact with the impossible, evidence that the universe is far more richly interconnected than we had dared to believe. As astronomical surveys continue to map the cosmos with ever greater precision, as theoretical physicists develop new frameworks for understanding the fundamental nature of reality, as computer simulations probe the deepest implications of our physical theories, we carry with us the knowledge that the universe has already shown us something that should not exist according to our understanding of natural law. In the southern sky, in a region of space colder and emptier than it has any right to be, according to the standard model of cosmology, lies proof that reality extends beyond the boundaries of our direct experience. The cold spot is not simply a scientific anomaly to be catalogued and explained. It is a cosmic memoir, a permanent reminder etched into the fabric of space-time itself that the universe is far stranger, far more wonderful, and far more mysterious than we can possibly comprehend. The hole in the fabric of time persists, patient and eternal, waiting for human understanding to catch up with cosmic reality. It waits for us to develop new mathematics capable of describing multiverse physics, new instruments sensitive enough to detect the subtlest signatures of inter-universal contact, new conceptual frameworks broad enough to encompass the possibility that our universe is not alone. Until that day arrives, if it ever does, the cold spot remains what it has always been. A question mark written in the language of cosmic microwave radiation, a mystery that bridges the gap between what we know and what we can barely imagine. It stands as testament to the fact that the universe still holds secrets vast enough to humble human ambition, profound enough to reshape our understanding of existence itself. The cold spot teaches us that reality is not bound by our expectations or limited by our current understanding of physical law. It reminds us that the cosmos operates on scales of space and time that dwarf human experience, following principles that may forever elude complete comprehension. In contemplating this cosmic void, we are confronted with the ultimate question that has driven human inquiry since our species first looked up at the stars and wondered about our place in the grand scheme of existence. We are not merely observers of the universe. We are participants in its ongoing story of discovery and revelation. The cold spot represents one chapter in this story, but it is a chapter that suggests the book is far larger and more complex than we had ever imagined. Each page we turn reveals new mysteries, new questions, new reasons for wonder and humility in the face of cosmic immensity. In the end, perhaps the cold spot's greatest gift is not the answers it might eventually provide about multiverse physics or exotic cosmic phenomena, but the questions it forces us to ask about the nature of reality itself. It reminds us that we live in a universe far stranger and more magnificent than our ancestors could have conceived, a universe where impossible things leave their signatures in ancient light, where the fabric of space-time itself bears the scars of encounters with the unthinkable. The hole in time remains eternal and enigmatic, a cosmic invitation to keep looking up at the stars and asking the questions that define us as conscious beings capable of wonder. In mapping this void, we have mapped something far more important: the boundaries of human knowledge and the infinite possibilities that lie beyond. The cold spot stands as both a monument to scientific achievement and a reminder of how much we have yet to learn about the cosmic story of which we are all a part. And so the mystery endures, written in photons that have traveled for nearly 14 billion years to reach our telescopes, carrying within their wavelengths the signature of something that should not exist, but does. The map that revealed a hole in the fabric of time has also revealed something profound about ourselves, that we are creatures capable of detecting the impossible, of finding meaning in mystery, and of standing in awe before the infinite complexity of the cosmos that gave birth to consciousness itself. In that awe, in that wonder, in that endless questioning of reality's deepest nature, we find perhaps the most human response to the cold spot's cosmic riddle. We are the universe's way of knowing itself, and in studying this anomaly, we participate in the greatest story ever told, the story of existence